Hi, welcome to another lecture on differential equations. We are going to talk about systems of equations, and systems of equation connect to linear algebra. So I'm going to start doing a quick review of basics of linear algebra, and surely most of you are going to have an entire course on this topic. At this stage, we are just looking at the basics. So in our systems that we have looked at before, we come across expressions like this. We have a quantity x and y. They are changing, so we are interested in their derivatives. And perhaps the derivatives are simply related to the quantities themselves, such as x prime being, say, 2x plus 3y, and maybe y prime being 4x plus 5y, and so on. We have looked at this problem from the point of view of a substitution or elimination method. We are going to take another approach, more systematic to this thing, and look at it from the point of view of linear algebra. So you notice the numbers that are showing up here, this 2, 3, 5, we can record them in an array. And an array is just a rectangular arrangement of numbers. And essentially that problem just identifies with that array 2, 3, 4, 5. So we are going to learn how to deal with arrays, and then we come back and offer a quick way of solving these type of problems. So what kind of arrays can we have? Sometimes we have an array which we call a row vector. A row vector is, for example, several numbers written in a horizontal fashion. That's referred to as a row vector. A column vector, for example, could be a vertical arrangement of numbers. So, for example, 7 and 8. Square matrix as opposed to a rectangular matrix. So this is a square matrix because the dimensions of it in the horizontal and vertical directions they're the same numbers. Every array comes with a dimension. So if I have, for example, 2, 5, 7, 8, 9, 1, that the array of this thing is, this is of course 2 rows by 3 columns. So this is, we abbreviate this thing as 2 by 3. So the first number is how many rows we have, and the second one is how many columns we have. For a square matrix, the number of rows and columns are, of course, are the same. In that case, we have 2 by 3 matrix. Okay, a long-term plan of linear algebra is doing the entire field of calculus, but with matrices. Well, before you start doing that, you have to settle what do you mean by doing arithmetic with these entities. Well, what's arithmetic? Well, addition and subtraction, multiplication, division, power, and perhaps functions at the top, and they all enter. No surprises with respect to addition and subtraction. So if I have a vector, say 2, 3, and I want to add to it another vector, say 4, 5, and both of them are horizontal, I can simply add the first with first and second with second, and I'll be all done. So if they were both column vectors, same way. But we have to make sure that we don't mix and match. In some cases, that's not going to work. We have always the issue of compatibility when we are doing arithmetic with matrices. We want to make sure that what we want to do actually does make sense. For addition and subtraction, the dimensions of all vectors have to be the same. So the dimension, we said, is how many rows by how many columns we have, and we have a simple compatibility requirement for addition and subtraction, which is all the dimensions have to be the same. Okay, next up is the issue of multiplication. And at this stage, it all becomes more complicated as to, well, what do we actually mean by multiplication? Well, what could be meant? At this stage, we need to separate uh, scalars from any of these quantities. For example, matrices or vectors versus matrices or vectors. Scalars is a fancy name to all the numbers we have been using all along. So from the elementary school up to calculus, you're dealing with scalars, you just call them numbers. Now the question is, if I have a scalar and multiply by vector, what happens? For example, suppose I have 2 times a vector 5, 6. Well, this is essentially same as factorization or anything else you might have. So the answer is just obvious, 10 and 12. So it's same as adding this thing to itself, and there are going to be no surprises there. So if by multiplication you mean scalar, like this 2, multiply by a matrix like this vector 5, 6, we have no surprises there. But that is not very interesting. What is interesting is multiplication of vectors by vectors, or matrices by vectors, or matrices by matrices, and so on. And all of that comes down to something that you might have seen in several different courses, and that's the issue of the so-called dot product. Dot product, you might have seen it in your physics class. There might be a force vector and then a displacement vector, and then you dot them and you get the amount of work that is done. So that's from the point of view of applications in physics or engineering. Here, if you have a vector, let me write a vector like say 2, 3, 1, and a second vector, that this one is going to be a column vector, say 5, 6, and 2. What we mean by a dot product between these two, and we don't actually write the dot here, is that we multiply first element with the first one, so 2 times 5 plus 3 times 6 plus 1 times 2. So one explanation for this peculiar kind of multiplication is the following. Suppose you want to buy several fruits, say apples are 5 cents, bananas are 6 cents, and oranges are 2 cents. So if we have, say, apples, bananas, and oranges, and then, excuse me, let me rewrite this thing so it's a little bit bigger. So we can have one of these vectors for the prices, and the other one is your shopping list. So suppose I want to buy two apples, 3 bananas, and 1 orange, and the price of them was say 5 cents. So that's the price of apples, and 6 cents is the price of bananas, and 2 cents, say, that's price of oranges. Of course, you multiply the number that you want by the price of the item, and then you add them up to get a subtotal for yourself. So in this problem, it's going to be 10 and 18 plus 2. So for example, 30 cents and such. So think about the shopping list, how many items you want, and price of each item. You multiply these two, first with first, second with second, and third with third, and then you add them up. Now, in your physics classes or engineering classes, they might not insist to write these vectors in any particular way. They don't care about horizontal and vertical and such. That's fine for what we have in mind and what's going to come up next. That's the style that we are going to write it when we are dealing with matrices and arrays. So what are we learning now? Special kind of multiplication. If I have a row vector and a column vector after that, and the compatibility here is that they have the same number of entries in them. You cannot have 3 items on one and 2 items on the other one, or 4 items on the other one. That would not be defined. If there are same number of items on them, the first times first, second times second, third times third, and then you have to add them up. Now remember that output comes as a single number, like what you buy from the supermarket. At the end, you just have one single payment to make, and you don't want to write these things as loosely arranged with the commas or spaces and such. You just add them up, and that is the subtotal that you have. Okay, that is how you multiply two vectors. What if we have two matrices? How do we multiply them? Best example is to best method to handle this thing is just to have an example. Say I have 1, 2, 3, 4. So I say I have this matrix, and then I have another matrix. Let's write 5, 6, 7, 8. Well, what is meant by product of these two? Well, what it is going to be is a repeated act of taking rows from the first matrix. So here are my rows. Let's indicate them with red, and then let's take a second one and take them and break them up into columns. So column 1, column 2, and then here is of course row 1 and row 2. How do we multiply them? We multiply each row with each column according to this dot product that we had here, and then arrange the output in a location that is inherited from the row and column position. What do we mean by that? Let's just go ahead and do this thing. So I'm going to indicate schematically what I'm going to do, and then I'm going to do it. So I'm going to take row 1 and column 1 and multiply them and write it in spot that is first row, first column here. Row 1, column 2, row 1, column 2. I am going to multiply them in that style that we did here and write it here. And then I'm going to do row 2, column 1, and then I'm going to do row 2, column 2. Excuse me, column 2. Let me. Okay, done. That is the plan of action. You notice that it's quite a bit of multiplication and addition, so it is intensive in the sense that number of arithmetic steps that we have to carry out to do these things is going to be high. And this is just 2 by 2. It's almost the smallest example we can make up. So imagine that if it was 10 by 10 and it was some other size, perhaps another 10 by 10, then you'll have 100 of these things to do, and each of them is a product of a vector with 10 entries with another 10 entries. So it gradually builds up, and all of a sudden you're doing 1000 multiplication. So let's just, for the sake of practice, perhaps you want to pause this thing and figure this out yourself, and then come back. So I'll have 1 times 5, 2 times 4, added up 5 and 14, so I'll have 19 here. 6 and 16, so I'll have 22 here. 3 times 5, that is 15. 4 times 7, that is 28. So I have 43 here. 3 times 6, that's 18. 4 times 8, that is 32. And then it appears to have I have 50 here, and so on. So well, what is the compatibility condition? The compatibility condition is that when you want to multiply this with that, the numbers should match. So number of columns that you have here number of rows that you have here, they have to match for you to actually be able to multiply. So number of columns of first matrix should be equal to the number of rows of second matrix for you to be able to carry out. Now, we don't want to get sidetracked with all the lengthy arithmetic, and it's a basic thing. Let's just to concentrate on the procedure itself as opposed to numbers. So here's a question. If I have a matrix, and now I don't write down the numbers, rather I just put some star for um, reserving a location for that. And then I have a second matrix, and this one looks like this. Can I multiply them? So that was compatibility condition of multiplication. It might be a bit confusing try to memorize this thing, so I suggest you instead try to actually think about this thing visually. You want to take this column, and then you want to actually that row, and you want to multiply by that column. Well, are they compatible for multiplication? Which means, do they have the same number of entries in them? No, they don't. This is 3 items, this is 2 items. I cannot do a dot between these two. So here I just write that such a thing is not defined. What if the other way around? Suppose I had 2 here, and then I had the following as a second entry. Would that work? Well, I have to take a row of this, and I have to take a column of that. Can I multiply them? Yeah, well, yes, I can. First with first, second with second, and everything works out. So if I do multiply them, what kind of matrix do I get? What's the output of that? Well, first row, first column, that would be some entry. First row, second column, first row, third column, and second row, same thing. So now the result of multiplying these two is going to be a 2 by 3 matrix. Okay, so that is a very brief introduction to multiplication. As we go to the other entries on this list, the procedures become more complicated. That notation actually doesn't get to be used. Instead, they use the notation of inverse, and powers come up later, and functions come up later. Now, that should be enough to get us started with some basic facts about matrices, and then we come back and mention perhaps these other operations as well. So okay, next we want to go and practice some basic systems of equations. So these are like systems that you have seen in like Algebra 1, Algebra 2, and so on. Let's start with very simple systems. So we are going back to systems. This is systems of for ordinary numbers. So suppose you have equation x plus y equal to 2, and say x minus y equal to 0. We know various ways of solving this type of systems, like elimination, substitution, Kramer's rule, and so on. Let's go ahead and take a look at this thing from a point of view of geometry. Like each of these equations is the equation of a line in a plane. So x plus y equal to 2. So that is obviously a line whose x and y intercepts are 2, and well, that's how it looks like. This is x plus y equal to 2. Second one, well, that's just y equal to x. The second one is just looking like this, y minus x, or x minus y equal to 0. Well, what is meant by solution? You can easily see here that the solution is 1 and 1, 1 and 1. Sum is 2 and difference is 0. And that happens to be just exactly this point. That's point 1 and 1. So one thing we remember is that the solution of a system it corresponds to the intersection common point of all the plots that we have. Well, that is going to give us an idea. If we have a system, it corresponds to, if it's in two variables, corresponds to two lines. Well, what can happen with two lines? It can be one of the variety of cases, one of three cases. If you have two lines, either something like this happens, and then there is an intersection, or you have two lines and then one of them is happening to be parallel to the other one. And a third case that happens, rather extreme, is that you have one line and the other one happens to be right on top of the first one. So either the two lines intersect or they don't intersect at all, or every point of their being there is an intersection. So if we were going to count how many solutions we have for a system that gave these equations, here we say, well, there's one solution. In this case, there is no solution. In this case, there are infinitely many solutions. That is, every point is a solution. So no solution, we can call it zero solution, meaning the number of solution is zero. So sometimes this is referred to as 0-1 infinity theorem. We looked at it from a very simple perspective of just two lines, but it so happens that it applies to any kind of a linear system, regardless of how many variables you have and how many equations you have and so on. One of three things happens. Either you have no solution like this, or you have exactly one solution or a unique solution just like that, or you have infinitely many solutions that is like this. Let's go ahead and write an example for this one. For the first one, well, we have this case, and that is the one that gets to be emphasized quite a bit in the elementary algebra classes and so on. This is more or less what you see all the time. But in fact, what we have in mind is these two cases. Let's go ahead make up an example for this one. Suppose I have a system of equation that looks like, say, 2x plus 3y is equal to 6, and the other one is, say, 4x plus, say, 6y is equal to, let's say, 18. How do we know that this system doesn't have a solution? Would you want to pause for a second and guess for yourself? Why is it that this is a system that has no solution? You can see easily, if you compare the left-hand side of this equation, what has happened from the first to the second? Of course, this is just a double of that. But how about the right-hand side? This is a 6, this is a 18. We have doubled the left, but tripled the right. So if there is any x and y that gives you 6, if you double them, it's not going to give you 18, it's going to give you 12. So this one doesn't have a solution. If you were to graph this first equation, what does that give you? First equation is x-intercept of it is 3, of course, and a y-intercept of it is 2. So the first equation that you have there is this, 2x plus 3y equal to 6, represents such a thing. How about the second one? Well, x-intercept of it is 4.5, y-intercept of it is 3, and if you graph the other one, you see that it looks like this: 4x plus 6y is equal to 18. These two happen to be parallel to each other. How about a case like this? Well, if I had 2x plus 3y is equal to 6, and then 4x plus 6y is equal to 12, obviously I've taken the left hand side the double, the right hand side also double. So this equation encodes exactly what this one did. There's no new information here that wasn't there. If you draw them, the first and second equation, first equation just like what we had here, and the second equation, again, the x and y intercepts are the same. It's exactly the same line. The equation of it just multiplied by some multiple, and whatever x and y that works for one of these equations is going to work for the other one, and there are infinitely many of them. For example, if you have let's say if you have your x is 3 and y is 0, of course that's a solution. If your x is 0, y is 2 is a solution. You can choose x and y anything that you want, and then you find the other one correspondingly. Now the question is, what is a telltale sign of a system that will differentiate these cases? Before we go there, let's go ahead, take a look at another example. Suppose I take, let's say, 2x plus 3y is equal to 0, and then 4x plus 6y is equal to 0. And this one versus, suppose I take 2x plus 3y is equal to 0, and then 4x plus, say, 7y is equal to 0. How many solutions do each of these equations have? What are the possible solutions? One solution that strikes us from the outset for both of them is that x equal to 0, y equal to 0 is a solution. So what's special here? I have taken a right hand side and made them to be 0. And that is, in linear algebra, this kind of equations are called homogeneous. So the constant portion is all made into 0. If your system is homogeneous, variables equal to 0 is always a solution. We don't need to work hard to figure that out. And for that reason, this is called the trivial solution. That's, of course it is so. If right hand side is 0, well, if you take all of your variables to be 0, then that's obviously true that it solves it. The question is, other than trivial solution, is there any other solution? These two cases are very different. How is that? This one, whatever x and y you find fits also into the second equation, because this is simply the double of that. So if you find an x like 3 and y equal to, say, minus 2, solves this. Exact same set of numbers solves this one. You can find another number such as 6 here and minus 4 there. That also fits here. This system has infinitely many solutions to it. How about this one? For example, find x from the first equation. So you can say x is equal to minus 3 half of y. Put it in the second equation. Multiply this thing by 4. It makes it minus 6 of y plus 7y is equal to 0. So that boils down to y equal to 0, and therefore x also equal to 0. So when you actually go ahead and solve this system with any of the methods you know, the only solution is 0, 0. This one has only one solution, which is just that trivial solution. There's nothing else. However, this one, other than the trivial solution, there's a whole slew of other possibilities. They are all possible cases for us. Of all these cases, what is going to be most significant, important to us is the following. Under what conditions would a homogeneous system have infinitely many solutions or have anything other than trivial? Can you see how? Well, this is all multiples of each other, and one way to check that is that if you multiply these two and subtract the product of those two, you get 0. So the fact that they are proportional is that 2/4 is equal to 3/6. How would you have checked fractions back in middle school to make them, to compare them? You multiply by the common denominator. So you multiply by 2 times 6 and then 3 times 4. That means statement that these two fractions are equal to each other. Or 2 times 6 minus 3 times 4 actually turns out to be 0. Well, that is our criterion. If I have ax plus by is equal to 0 and cx plus dy is equal to 0, a, b, c, d will be some numbers like these. To have the possibility of having something other than the trivial solution, what I need is for these two equations to be proportional to each other. And the easiest way of measuring that is by the so-called determinant. So determinant for this system is going to be, so determinant is AD minus BC. Determinant of a 2 by 2 system is AD minus BC. You write the equations underneath each other in the same order of x and y. Cross multiply the coefficients and subtract, and that is going to be our determinant. So what we have is the following. If I have a matrix with the entries A, B, C, D, I define the determinant of it as AD minus BC. Sometimes books refer to these matrices perhaps by a letter like M, and they might talk about determinant of M. Some of them might indicate it in this fashion, or some other notations for indicating that they are dealing with determinants. So let's learn the following. For a linear homogeneous system to have infinitely many solutions, or to have any solutions other than the trivial solution, its determinant has to be 0. That's a crucial fact. So suppose I give you the following problem. Say I have 5x plus 6y is equal to 0, and say 7x plus ky equal to 0. And then I ask what should be the values of k so that the system has infinitely many solutions. K should be equal to what? So that system has infinitely many solutions. Well, I say, well, what is the determinant of this system? Determinant 5k minus 6 times 7. I want this to be 0, so 5k has to be 42. So my k has to be 42/5. K has to be 42/5 so that my system has infinitely many solutions. Okay, you might be wondering, what do any of this has to do with differential equations? We said our objective is to study systems of differential equations. We had seen this kind of things. For example, we studied the multi-tank systems that had a set of equations like these. Now, what we want to do is attempt to solve some of these systems. Let's see how do we proceed. Okay, let's go consider a system of differential equation and see how we can solve it. So suppose x indicates some function of t and y also indicates some function of t, and of course x prime is shorthand for dx dt, and y prime is also a shorthand for dy dt. And suppose I have a system that says x prime is equal to 1x and then 2y, and then y prime is equal to, say, 4x plus 3y. Of course, normally we don't write a 1 as a multiple, but I just wrote it so that we see how our matrix is looking in this case. Now, x prime, y prime, we can compress it into a vector and then put the prime outside, meaning a prime of a vector means prime of each of the components of it. 1, 2, 3, 4, we can put them into a matrix. 4, 3, I wrote it like this, 4, 3, times x, y. You remember how we did the multiplication. We had, we said we take a row and then we take a column. So this red row with the blue column, we multiplied 1 times x and 2 times y. That's what this is. And 4 times x plus 3 times y, that's what the second equation reads like. So the general pattern here is that on the left hand side we have some vector, let's call it the vector v, whose derivative is being taken, and here I have some matrix, and then here is that same vector v. You remember at the very beginning of the semester we had this kind of equations. For example, we write y prime is equal to 2y or y prime is equal to 3y, and we solve it. And first act that we had was to look for exponential solutions, that is x and y were certain function of lambda. So here I'm going to assume, then we are going to go ahead and verify that x is some, I don't know what, exponential of lambda t, and the y is some other. Okay, so y will be some b times exponential of lambda t. We are going to go ahead, try to find solutions of this type, just like what we did at the beginning of the semester, for equation that look like that. So what is x prime? Derivative with respect to t of this thing will be a lambda exponential of lambda t. Right hand side I have 1x, so 1a exponential of lambda t, 2y, that will be 2b exponential of lambda t. On the second row I have b times y prime will be b lambda exponential of lambda t. Right hand side I will have 4a exponential of lambda t, and then 3b exponential of lambda t. So if lambda t, exponential of lambda t, wants to solve this equation, it has to fit in this format. Now I look at this thing and see I have exponential of lambda t everywhere. I divide by that and I get something a lot less cluttered. So it becomes a lambda is equal to 1a plus 2b, and here I have b lambda is equal to 4a plus 3b. Let's go ahead and write this thing in a matrix format. The right hand side is 1, 2, 4, 3, and then times AB. Is that right? All of this is 1, 2, 4, 3 times AB. Right hand side, I can write it as lambda times AB. Is that right? This transformation from one form to the other one is very important. Now, this ingredients of these equations are so important. They often show up in so many places that each piece has a name. This number lambda that turns out to be the number that solves our main ingredient of our system is called the eigenvalue. Here we are using it for solving differential equation, but the same concept shows up in many other places, and it's given a name. It's called eigenvalue. Eigen is German for special, so this is a special value, a special number that is connected to this matrix. This is eigenvalue of that matrix that you have 1, 2, 4, 3. And then also on this pair of numbers a, b that magically solved the problem for us, that also has a name. This is called an eigenvector of the same matrix. And each eigenvector goes with a certain eigenvalue, so they pair to each other. This is an eigenvalue of the matrix, is an eigenvector of the matrix, and these are like siblings of each other. Okay, now we want to actually go ahead and find all these three things, a, b, and this lambda. From the outset, pay attention to that if I find a and b as some numbers, then if I double them, that's also a number. If I triple them, that's also a number, and so on. Also notice that a and b equal to 0 is always a solution, but then that is like saying x equal to 0, y equal to 0 is a solution. So we are going to exclude that solution as a trivial or as a useless solution. So in our solutions, we always search for a and b so that they are not both of them at the same time 0. That doesn't give any kind of information to us. So how do we find all of these things? I'm going to take this equation and rearrange it here. So I take a lambda to the right hand side, so it was 1a, and then I subtract lambda a, and then I had 2b that's equal to 0, and then in the next line I have 4a, and then I have 3b minus b lambda, or lambda b equal to 0. Let's go ahead and factor. So I have 1 minus lambda times a plus 2b equal to 0. And here I have 4a plus 3 minus lambda times b equal to 0. So that matrix 1, 2, 4, 3 that I had, 1, 2, 4, 3, I have just subtracted the lambda from this so-called the diagonal of that matrix. Now you remember what we said before, that if you have a system and you want to make sure that it has a non-trivial solution, then its determinant has to be 0. Sorry for that. So where was it? Yes, here. If you have a system and you want to make sure that you have non-trivial solutions to it, the determinant of it has to be 0. So here I need the determinant of, now what is my matrix, is 1 minus lambda, 2, 4, and 3 minus lambda. That I want to have to be 0, so that I can find non-trivial solutions for a, b. If this is not the case, then a, b, both of them I'll be forced to be 0. I don't want that. That doesn't give me any new insight or anything. So I need to have the determinant to be 0. Well, what was the determinant? Take these two, take those two, and multiply them. So I get 1 minus lambda times 3 minus lambda, and minus 2 times 4 equal to 0. So that was the determinant of that matrix. Well, that's a simple equation. Let's multiply lambda squared minus 3 lambda minus lambda plus 3 minus 6 is equal to 0. Excuse me, of course, 8 equal to 0. So lambda squared minus 4 lambda 3 minus 8 is a 5. Sorry, let me correct these things. So this one is a nice equation. So I have easy roots. So I got two eigenvalues, lambda equal to 5, lambda equals to minus 1. It is customary to go ahead and number them, number 1, number 2, or the larger one and a smaller one, and somehow. So for example, you can this is the first eigenvalue and this is the second eigenvalue. You can order them in any manner that you want. Corresponding to each of them, then we can go ahead and find out what A, B would fit. So once I have my lambda, I pick one of them, put it in my equation, and then go ahead and find out what A and B are going to fit in that equation. Again, we are not going to find a specific value for A and B, rather we are going to find a ratio for them, and that is good enough. So let's take the first one, lambda 1 equal to 5. I am going to put it in this equation. Let me write this equation again. So let's paraphrase what happened. This was the matrix. Then from that we made 1 minus lambda, 2, 4, 3 minus lambda. We made the determinant out of it and then found the roots of that. So this is the root. Now I take one of these roots, like 5. I put it here, 1 minus 5, 2, 4, 3, 3 minus 5. Let's simplify. It becomes minus 4, 2, 4, minus 2. You notice that our rows are very peculiar, or our columns are very peculiar. One is a multiple of the other one. For example, if you take this multiplied by minus 1, you get that one. That's always the case. This is not an accident. Specialty of lambda that always does it, that for 2 by 2 matrices, the resulting matrix are going to be, the rows are going to be proportional, or the columns are going to be proportional. Now what is our equation? This was, you remember, that was after you put the lambda here, the right hand side has to be 0. We go back to that equation. So I have minus 4a plus 2b equal to 0, and the other one is 4a minus 2b equal to 0. Now notice that one of these equations is redundant. You can throw away whichever you want. This is simply that one multiplied by minus 1, or vice versa. So you can, for 2 by 2, we can always throw away one of these equations. Well, how about the other one? If you have minus 4a plus 2b equal to 0, that means 4a is equal to 2b, or that means 2a is equal to b. Now what is a and b? We don't get specific numbers. You have a choice. For example, if b is 1, a will be 1/2. Well, what if my b is 2? b is 2, a is going to be 1. So ab, you can have 1/2, 1, or you can have 1, 2, or you can have, instead of b, you can choose 4, a will be 2, and so on. Do you agree with me that the nicest one of these is this one? First of all, we don't like fractions, and second, we also don't like unnecessarily large numbers. So 1, 2 is going to be fine. So let's record it for ourselves. One eigenvalue, I got 5, and the corresponding to this thing, let's call it number 1, a and b became 1 and 2. What does this mean? It means x a lambda t, so it's going to be 1 exponential of 5t, and y is equal to 2 exponential of 5t. This solves our equation. What's the name of these things? Called eigenvalue. This is called an eigenvector. An eigenvector is representative of a whole list of them. Yeah, any of them would do. Then we have to repeat all of this all over again for each eigenvalue we have found. So now our second eigenvalue is -1. So again we repeat. After you solve a few of these things, the process will be much faster. 1, 2, 3, 4, 3. You remember we subtracted the lambda from the diagonal, so I'm just repeating it for the sake of practice. Now here our lambda was 5. Here our lambda is -1. So when I put -1, this becomes 2, 2, 4, 3 minus -1. What was that? 4. You remember what we said last time. The rows have to be proportional. The columns have to be proportional. Notice this is twice as large as that. Next, we are going to do what? We are going to solve this. It's going to be 2a plus 2b equal to 0, and 4a plus 4b is equal to 0. Of course, the solution that we get here is that a is simply equal to -b. So if I want to make a matrix AB, here's a choice. Take B to be 1 and A will be -1, or vice versa. Of course, I could have taken -2 and 2. I could have taken 2 and -2. I could have taken all of these things, but we can reason it that that is the best. So our second solution then here turned out to be the following. So lambda 2 became -1, and my eigenvector number 2 became -1 and 1. So that tells me x can be a is -1 exponential of -1t. That's my eigenvalue. And y is b, which is 1 exponential of -1t. We found two solutions. So this is a solution, that is a solution, and as it turns out, any linear combination of them will be a solution. So I can write my solution like this: x and y, any multiple of the first one. So c1 times this, so c1, what was it, 1, 2, exponential of 5t, and then c2 -1, 1 exponential of -t. This is solution of x prime, what was it, 1x plus 2y. Y prime was 4x plus 3y. What is going to determine the C1 and C2? You can apply your initial conditions, if you have initial conditions, to get your C1 and C2. Okay, so we compressed linear algebra and its application to differential equation into one lecture, so it's a rather dense lecture. Let's see what happens. Let's go from the beginning. So we talked about arrays and row vectors, column vectors, and matrices. Pretty much all the time we are working with square matrices. We said we are planning to solve systems of equations. So we learned about addition, subtraction, and multiplication of matrices. The interesting one was how to multiply two matrices. We used it primarily for writing our systems of equations. So we had the compatibility condition, but most often items we deal with are compatible. Then we went back to systems of equations. We noticed that a system can have one solution, which is what you probably have seen oftentimes in high school. Sometimes it has no solutions, and sometimes it has infinitely many solutions. Of these, the case of infinitely many solution is the one that is of most interest to us. Here we consider the homogeneous system. We said homogeneous always has a solution, which is all variables equal to 0. The question is there any non-trivial solution to that? And the only the condition that is theoretically easy to apply is that the determinant of your system has to be 0. So determinant has to be 0, and then you will be granted non-trivial solutions. That is the important observation. Determinant 0 gives us non-trivial solution. So here we practiced how to solve one system of equations. So I have a system. I write it with matrix notation. Here is the application of the matrix notation we had up there. In order to solve it, we'll search for exponential solution. We consider x and y be some multiple of exponential of lambda t. We plug it in, and we get an equation that is like a system of equation we have seen before. We said the ingredients here are so important. They have their own names. That lambda is called eigenvalue, and the vector is called an eigenvector. We brought everything to one side and asked for determinant to be 0. Here we set the determinant equal to 0. We get a polynomial equation. As usual, this is called the characteristic equation. Sometimes lambdas are called characteristic roots. We find them. In this case, they were friendly, whole numbers, real numbers, distinct numbers, and that is all very special. That makes our life a lot easier. Okay, and then we found our lambdas. We put the lambdas in our system. We get our A and B, and A and B are going to give us one possible solution. We repeat this process for each eigenvalue. We get a second solution. Now a linear combination of the two solutions multiplied by C1 and C2 is going to give a so-called general solution of our system. How about C1 and C2? Well, you will want initial conditions to figure those items out. Okay, until next time, good luck and God bless.